Welcome back to MA 760 Engineering Analysis 1. Last time as we stated before in the last lecture, we will divert from the book a little bit up to the end of this topic, the matrices and linear algebra. So we discussed last time the spectral radius for a matrices, and we showed that the spectral radius is defined as the largest eigenvalue for the matrix, and also we stated last time that if the matrix has a unique, distinct eigenvalues, we can apply the power method to get the eigenvalues through the iterative technique. And we showed last time that, okay, if we have the iterative technique and you pick up initial guess for the vector x, which is a linear combination of your eigenvectors for the matrix of interest, matrix A, for example, you will be able to converge to the right spectral radius, which is the largest eigenvalue. So is there another way, for example, to estimate the spectral radius not based on iteration? Yes, there is a method here that we will be going through. It's called Gershgorin's theorem, and I will show you in a minute here. But before I start, some of you asked me that for the homework problem, if you have something like 1 over the square root of 8 multiplied by your matrix, when you get the determinants of this, whether it will be 1 over 8 or 1 over 8 to the power of cube or whatever. So if you remember, if you have a matrix, let's say 2 by 2 matrix, so this is A11, this is A12, this is A21, and this is A22. If you have a constant C here, this is, you said that, okay, I will multiply C by all the elements, so this will be C A11, C A12, C A21, and C A22. And this is to say that to get the determinants of this will be, let's say, this is matrix A. So the determinants of matrix A is nothing more than C A11 multiplied by C A22 minus C A12 multiplied by C A21. So when you get it like this, so this is nothing more than C squared, this is nothing more than C squared, so it is C squared multiplied by your determinant. So what I want to say here, is, if you have a 2 by 2 matrix and there is something like a constant multiplied by the matrix outside, so when you get the determinant, if it is 2 by 2, you will raise it to the second power. If it is 3 by 3, you will raise it to the third power. If it is 4 by 4, you will raise it to the fourth power, and so on. Just to let you know in future. So now let's go back again to the spectral radius. And again, the spectral radius, why we are interested in the spectral radius in the first place. Because as we stated last time, the spectral radius is of interest in the iterative schemes for solving the large sparse system of linear algebraic equations. So if you have a matrix which is, let's say, 1,000,000 by 1,000,000, you are not going to use the Gauss elimination technique because it's very tough and very time consuming, and maybe it's beyond the capability of computers to do something like 1,000,000,000 by 1,000,000,000. So you have to do the iterative scheme and the iterative technique that we will be discussing this lecture that will converge only when the spectral value or spectral radius of the matrix is less than 1. So last time we showed a simple example where we found out that the spectral radius was 4. So let's discuss a geometrical way of giving us an upper bound, let's say, for the spectral radius. And this is called Gershgorin's theorem. Again, this material is not in the book. And the theorem states that all eigenvalues of n by n matrix A, where A is just A jk, or in the union of n disks, or call it circles, of those disks are defined by this mathematical formula here, and in a minute I will show you what I mean by this formula, where k equal to 1 up to n. So what does it mean? So let's assume that the matrix A is very sparse matrix, for example. Then I have A11, A12, up to A1n. Then this is A21, A22, A2n, A31, A32, A33, up to A3n. Let's assume that this is the row J, so this is AG1, AG2, up to AJ, AGN, here is ANN, and this is AN1, and so on. So this is the diagonal here, will be the diagonal for the matrix. So what this theorem states is, if you have an eigenvalue problem, A lambda j equal to lambda j mu j, all what says this is the eigenvalue problem. Those are the eigenvalues, and those are the eigenvectors of the matrix A. The eigenvalue, because we did not say anything about the eigenvalues, they might be real or they might be complex. If they are complex, I can put them in a complex plane where this is just the imaginary of certain complex number z, and this is the real of the complex number z. So all what the theory states is, if you look at the jth row, and you take the diagonal element in the jth row, AJJ, and this is, if this is a matrix, if this matrix is complex matrix, for example, AJJ will be represented by what in the complex plane? If you have a number, complex number, how you will present it in a complex plane? As a what? As a point in the complex plane. So this would be what? A point here, where this is AJJ, because it has components. It has a real and a complex component. Then this will be just the amplitude of AJJ. So if you plot a circle around this AJJ, where the radius of this circle is just the summation of the off-diagonal elements of the row number j. So this is where k not equal to j, summation of a, j, k, and this is the amplitude of this. So what's this telling me is AJJ will be the center of this disk. We'll call it circle or disk. We'll call this circle or disk. So AJJ will be the center. Then if you sum all, excuse me, excuse me, if you sum all the off diagonal, so those are the off diagonal, those are the off diagonal of this row number j. So if you sum all those elements here plus here, this will give you a number. Maybe it will be, of course it will be a positive because I take the amplitude of the each one of those. So if this number, for example, is a complex number, let's say 3 minus 2j, and there is another one 3 plus 2j, and there is 5, and there is 10, and so on. All those numbers here will be each elements of the off-diagonal. So when you do the summation of the amplitude of every one of those off-diagonals, it will give you a real number. Yes, so this real number, just you will take it from, make the center is AJJ, and then plot a circle around it. So this circle, we'll call it disk. So this theorem states that the lambda j, which is corresponding to the jth eigenvector uj, should be somewhere here inside this disk. So if we pick up another row, let's call it AII, for example, maybe I will have another disk here. If I pick up another row, maybe I will have another disk here. If I pick up another row, another disk here, another disk here, and so on. So this is very nice representation, geometrical representation. What it says if you want to know where are your eigenvalues of the problem, all what you will do is what you will plot the AJJs, the rows, all the diagonals of your matrix in a complex plane like this, and then around each one of AJJ, just to get the off diagonal, the summation of the amplitude of the off diagonal, this will give you the radius of this circle. So in each one of those circles, so here I will have what? The eigenvalue j. Let's say that this is AII, so this will be lambda I. Let's say this is A11, so I have lambda 1 somewhere inside here. This is A22, so I will have lambda 2 here. This is A33, so I'll have lambda 3 here inside this circle here. So this is a very neat method to figure out where are the eigenvalues. So the total eigenvalues, all the eigenvalues will be the union of all those disks. Those are the eigenvalues of the problem. So this is very neat. From, yes?
And their expression for the circuit, the disk?
So, no, I will show it to you the expression. Yeah, I will show to you the expression. So, you mean here? Yeah, this is AJJ. Sorry, I'm sorry. So this is Z minus AJJ, and this is AJK. So let's do the proof now for this theory. So AU is nothing more than lambda U. This is the eigenvalue problem. And let's pick up the jth component of the eigenvalue. So this will give me A Uj equal to lambda j Uj. And again, so A Uj is nothing more than the summation of A jk multiplied by uk, and k goes from 1 up to n, and this is equal to lambda j uj. So now I can decompose this. This is all the summation of all the AJK multiplied by UK. So I can pick up from this, I can make it like summation of AJK UK when K does not equal to J plus the AJJ UK equal to lambda J UJ. Yes, guys? When J equal to K, I separate it here. Then you will bring this one in the other direction. So this will give you K naught equal to J, AJK, UK equal to lambda J, excuse me, minus AJJ. And when J equal to K, so I will remove this and I put J here. So this will be equal to UJ. Now, if I will take the amplitude of both sides, and I also have the freedom to pick up whatever row of interest. So here I have this matrix. I can from the beginning pick up J to be 2. So it will be the second row. Pick up J to be 1. Pick up J to be 3. Pick up J to be whatever. Pick up J to be any row. So in principle, I will pick up or choose J that will give me the maximum value of the all component of the vector U. So this will be the maximum of K of UK. So assume like your vector is like this: 1, 5, 7, 3, negative 20, 0 and 10. 1, 2, 3, 4, 5, 6, 7. So your vector U has how many components? 7 components. And it is equal to what? U1, let's say U1, it has 7 components, U1 up to U7. So I can pick up any J, but in this case I will pick up the J that will give me the maximum of all component, of the amplitude of all components. So what's the maximum for the amplitude of all components? Because you will take the amplitude of minus 20, it is 20. So this is number 5. So number 5 gives me the maximum. So I will pick up J so that the amplitude of the components of the vector are the maximum. So this is the J I will pick up. I will look at all the eigenvectors and I will look up the eigenvectors and I will look up where is the maximum component for this eigenvector. So I will pick up J to be corresponding to this one. Now, after taking the amplitude, I will take the amplitude for the equation, the above equation here, the second from below. So this will be lambda minus AJJ, and I will take the amplitude of UJ equal to the amplitude of the summation for K not equal J AJK multiplied by UK. But this is less than or equal to the summation of J not equal to K of AJK UK. So this is just the Schwarz inequality that we take last time. If you have the summation of all the components here and you take the amplitude of this, all the summations, this amplitude should be less than when you take the summation of the absolute values or the norm of the amplitude of the components. And you can just do something like a vector U with 3 or 4 components and make the components real or imaginary and try to add those together. You will notice that this holds. So it is either equal to this or less than this. So this inequality is here. But we picked up uj to give us the maximum component. We picked up j to give us the maximum component of u. So if we replace uk by uj, still this will hold because uj is the largest. Yes? So if uj, you replace this one by uj here, so you are multiplying by something bigger, so the less than or equal is still holding. Yes? So we will replace uj by uk, so this will be less than or equal to j not equal to k multiplied by summation of ajk uj. So uj will cancel from here with uj will cancel from here, and we will end up with lambda minus ajj. The amplitude value of this is less than or equal to the summation when j not equal to k of ajk. So what's this? This is just the proof. What does it mean? So all those circles that we see here, the equation of all those circles is just z minus ajj. So if a point here is z and this is ajj, so z minus ajj is just the amplitude value, is just the radius. Yes? So in this case, this radius should be equal to what? Summation j not equal to k ajk. So if now lambda is here, so lambda minus, this is lambda minus ajj, which is this difference, is less than the radius. This means that lambda is inside the disk. And this is the proof for the theory here. And this argument will hold for all and every lambda j for the matrix A. So isn't it neat, just by looking at the matrix that I just cleared 5 minutes ago, you look the matrix elements, and then you will look at all those elements, and just by visual inspection of the elements and the summation of those elements, and by looking at the complex plane, you will say, okay, I have the diagonal here, diagonal here, diagonal here, diagonal here. This is the radius around each one of those diagonals, so I will have my lambdas, the eigenvectors, eigenvalues within these places. So this is very neat. So what are the consequences of this theorem? So consequences of Gershgorin theorem. So first thing is to estimate the spectral radius. So the theorem states that you will find in any of those disks around the diagonal elements of the matrix, you will find the eigenvalues. But it does not tell me which one is the spectral radius. The spectral radius is defined as what? The largest eigenvalue. So let's assume that I have the complex plane again here. So this is the real and this is the imaginary. And I have ajj here. So this is ajj. And then this ajj, I have the summation of the off-diagonal elements will give me a circle like this. So I can write or draw a bigger circle like this that's composed of what? Ajj plus what? This is the summation of j not equal to k of ajk. This part here, which is the same like this part. So, and I will call this radius rj. So rj is what? rj is just equal to this radius, which is ajj plus this part. And what's this part from this circle? Summation for j not equal to what? K of ajk. Okay, guys? But I can just recombine those again, and this will give me what? ajk and k equal to what? 1 to n, because I added everything. Last time I just decomposed those to two components. I recombine those two components again. So what does it mean? It means that for the first diagonal element, you got, excuse me, you got what? An upper bound for a radius called rj. Let's assume that the second component is here. ajj is here. ajj is here, and the spectral radius, the radius is like this, smaller one. So where the rj will be? rg will be here. Okay, so I have another rj here. Let's say I have 10 of those eigenvalues. How many rjs I will have? 10 rjs. So which one do you think will give me the upper bound for the spectral radius? The maximum, the largest. So exactly. So the spectral radius, as we defined it last time, mu of A will be just less than or equal the maximum over J of the spectral radius, which is the radius Rj, which is the summation of all the rows elements including the diagonal. So this is Ajk, where k equal 1 to k equal 1 to n. So this is just one of the consequences, and we will call it consequence number 1. So now let's assume that I have the matrix A and its transpose, A transpose, will have the same eigenvalue, same eigenvalues. Yes? The matrix and its transpose, they will have the same eigenvalue. So in this case, the spectral radius of the matrix A, we just define it as equal to the spectral radius of the transpose of the matrix, and this should be less than or equal to the maximum over J for the summation of all the jth column, k equal to 1 to n ajk, and then I will put transpose here because this is the A transpose. Yes, so it will be ajk transpose, and this will give me what? Maximum over J for the summation over k equal to 1 to n, and then what's the transpose of the element? Ajk will be akj. Yes, guys. So let's call this 2. So what does it mean here? What does this tell me? It's telling me that, okay, I can calculate the spectral radius of the matrix by looking for the maximum of Rj's based on the summation of the rows. So I will look for each row, then I will sum every row of the matrix, and I will look for the maximum of those summation. This will give me an upper bound for the spectral radius of the matrix. Yes? But this is telling me that I can do exactly the same but with the columns. So I will look for what? Each column, and I will add each column to get the at the end to get a value, and then picking up the maximum of each, the summation of each column, and this will give me an upper bound for what? For the spectral radius. So two methods, two techniques. Either sum all rows, so sum row number 1, this will give you value for lambda 1, row number 2, lambda 2, row number 3, lambda 3, row number n will give you lambda n, and figure out which one is the maximum. So this will give you an upper limit for what? For the spectral radius. Or you will go for the column number 1, add it, all the elements, and then this will give you lambda 1, add the second, look at the second column, so third column, fourth column, up to column number n, and this will give you values. Look for what is the maximum of those values, and this will give you also an upper bound for what? For the spectral radius. But what is the spectral radius now from those two techniques? It's just if we combine 1 and 2, we will notice that the spectral radius will be just less than or equal to the minimum from those two definitions. So the minimum from the first one, which is if you sum over all the rows, so this is AJK, and if you sum over all columns, so this is summation over columns now for AKJ. And so this is at least give you the least upper bound from both. So let's say you add the rows and you get the maximum is 5.3, and you add all the columns and you get 4.2. So which one will be the upper bound? 4.2. You take the minimum to be the upper bound for your spectral radius. Of course, other consequences of the theorem, if we have real and symmetric matrix. And early in the chapter, or in this linear algebra and matrices, we stated that the eigenvalues for your real and symmetric matrix will be what? Will be what? Real. So eigenvalues are real. Are real. What does it mean here in the complex plane to have a real excuse me, to have a real eigenvalues? What does it mean? So all the eigenvalues will lie in what? On the x-axis. So I will have, let's say, AJJ here with the circle or disk around it, AJJ maybe here, with another one here, another one here, another one here, another one here, and so on. And this is what? Summation when j is not equal to k for AJK, which is this diameter radius here. And this point here will give me an estimate of the lower bound for what? Lower bound for what? For lambda i's, because this is the smallest lambda I. Yes, this is the lower bound for lambda i's, because they are real. Yes, so this is the smallest lambda I. If you have lambda I negative, so let's say negative 20, and you have up to positive 100, this is the minimum lambda I in your solution. Okay, guys? So the theorem is just to tell you okay, what we want to do in order to figure out an upper bound, let's say, for the spectral radius. Now, we will be using the knowledge of the spectral radius in our technique for numerically solving a set of linear differential equations by the iterative technique, and this will be our next topic. So this is general iterative method. So again, to recast what I just stated at the very early beginning of the lecture, that it will be extremely unfeasible if you have a sparse matrix, for example, to use the Gaussian elimination technique to be able to solve the system of linear algebraic equations, for example. So it will be the best to use the iterative method, and now we will describe the iterative method. So if you have a system like AX equal to B, and we'll call this system star here. So the main goal for this iterative technique is to seek a matrix A wiggle. So the matrix A is very, very large, very sparse. If you want to solve for this, you will do what? X equal to A minus 1 B, yes? And in this case, if the matrix is very large, millions of elements, for example, rows and millions of columns, it's very, very difficult, if not impossible, to get the inverse of this matrix A. But let's say, if we can look for another matrix, A wiggle or A tilde, or whatever you name it, I know some of you are laughing, and this A wiggle or A tilde will simplify the solution so that the inversion will be much easier to perform. This is the trick here, and we will be using the iteration method. So I can get A tilde here, add A plus A tilde, for example, and this is the whole reason behind this, is to be able to use A plus A tilde and operate it over X. This is equal to B, and it will be easy to solve using this, easy to solve the system by just taking the inverse of A tilde multiplied by B. To give you an example that will clarify the idea behind choosing A tilde is if, for example, we decompose our matrix A to two components, a diagonal matrix and another matrix that does not have the diagonal but zeros everywhere. So if we decompose A to B, let's say, and it is easy to do something like this. If you have a diagonal matrix here, your original matrix, you will pick up the diagonal and everything will be 0, minus a matrix B, which will be all zeros in the diagonal, and then you will have off diagonal. And the off diagonal elements here will be what? Corresponding to the off diagonal here? Will be the negative of those off diagonal. Because you will multiply negative by those will be plus, then you will add it to add it to the zeros here will give you the same elements. So it's very easy to do something like this. Then this is the diagonal, and this is the zero diagonal one. Zero diagonal one. So let's pick up A tilde to be the matrix B. So now A plus A tilde multiplied by x equal to b. This is equal to what? What's a? D minus b. And what's a tilde? B equal to. So this will give you what? Dx equal to b and x equal to d minus 1 b. What's d? It's just a diagonal matrix. Yes? So what's the inverse of the diagonal matrix? Huh? So x will be equal to just the inverse of each element. So d11, 1 over d22, 1 over d33, 1 over dnn. That's it. Divided by b1, b2, b3. What do you think? Is it easy now to solve? Yeah, because x1 is equal to what? b1 divided by d11. And x2, b2 over d22. And so on. xn, bn over dnn. So this is a very neat way to pick up the correct a wiggle or a tilde so that you will be able to simplify your matrix and be able to solve the system of equations. So how we use, what's the use of a tilde? So we will look at the star equation ax equal to b and rewrite our star equation to be a plus a tilde multiplied by x equal to a tilde multiplied by x plus b. We just added a tilde to both sides. So just apply a tilde to both sides and that's it. So we added a to a, we added a tilde. So this would be a plus a tilde operated over b, and then b will be a x tilde, a tilde x plus b. This is coming from this. So those are, the two bars are equal, and you will end up with a equal to ax equal to b, which is the original star equation. So we did not do anything just by adding a tilde to both sides of the equation. So now, if I invert this equation, this will give me x equal to a plus a tilde minus 1 multiplied by a tilde x plus a plus a tilde minus 1 multiplied by b. So this is the matrix A tilde, the inverse of this matrix. And again, the main goal of our work is to pick up a tilde that will make my inversion very easy. So we decompose A, in the example here, we decompose A to be diagonal minus another matrix B, and we pick up A tilde to be B. So when we add those together, we end up with what? With a matrix D, that the inversion of this matrix D, which is diagonal, is very easy, and I showed to you here. So this is a matrix. This matrix, we will call it matrix G. And this matrix here, new matrix, we will call it matrix M, X. So X equal to MX plus G. We will call this equation double star. So if you look at equation like this, what's the best way to solve this equation? Iteration. You will start off with a guess for the vector x, then you will get what? Initial guess, then you will get the first one, you will take the first one, okay, and subtract it, let's say, from certain value, then you will get an error, for example, okay, if the error is very large, go back again and subtract it from, submit it here as the second guess, get the third, and take the third and submit it. So you will do this until, if you'll take two successive, let's say, two successive x's, and see the error or the difference between them. If you are going to, let's say, a very small value, so you are converging. If not, you are diverging. And this is the iteration technique, how to solve it. So sometimes, if you try to solve this numerically using the iterative technique, it will blow up, and it will not converge. This means that you did not pick up the right A tilde. So the main reason here is to pick up a right A tilde that will make it easy for us to do the inversion and so on. So you did not pick up the right A tilde. So I will stop here, and next time I will discuss with you the rest of this topic, and also prove to you that the conversions will not happen unless the maximum value of lambda of lambdas of the matrix A, which is the spectral radius, is less than 1. So this is the only way that you will have a convergence for this scheme. Do you have any questions so far?
You mentioned UK in the proof. What is that UK?
What do you say again?
In the proof of the first.
It's the kth eigenvector. UK is the kth eigenvector, because when we did this, we were doing summation of AJK multiplied by UK. This is from AU equals to lambda U. So when you try to apply AU equal to lambda U, what's the matrix component? AJK. And in order to get the matrix multiplication, if you have a matrix like this and a vector, we said that this is K1. So you have to have K equal to K, and it will end up with AJ1, which is AJ. Sorry, UJ. This is, you give you UJ.
So UK is the element of UJ.
Yeah, UK is the components of the vector.
Okay.
So I told you the example where we show that we have 7 components. So UK will be U1, U2, U3, U4 is the components of the eigenvectors K. And from matrix multiplication, you have to have, this is just, we can, instead of K, we can replace it K by I. Anything, any subscript will hold.
So it's the element of the J's.
No J. This is the the kth eigenvector, and those are, K will go from 1 to n. So this is just a running subscript. So when we have the summation here, we have K goes from 1 to n. So K runs from 1 to n. So this will be AJ1 U1 plus AJ2 U2 plus AJ3 U3 plus AJ4 U4 up to AJN UN. And when you get this summation, this will give you what? The eigenvector J, UJ. The jth eigenvector. Maybe after the class I will show it to you. Okay, any other question? Okay. Thank you so much. We'll see you next week.